Okay, so here's another interesting and important application. R2 is not homeomorphic to R3. Okay, so you'll probably recall that we show R is not homeomorphic to R2 by puncturing a point and seeing in one case you're connected and in the other case you're not. Here instead you look at being simply connected or not simply connected. I have not formally defined that term, but it's just having fundamental group non-trivial. We will shortly define that. Okay, so proof is that, so let f from, let's say, so let f from, let's say, R2 to R3 be a homeomorphism, and we'll get a contradiction. Okay, without loss of generality, we can say that f of the origin is the origin in R3. Okay, so R2 minus the origin, the set which is a singleton, is mapped by f. This is a homeomorphism to R3 minus the origin. This is achieved by maybe post composition 0, 0, 0. Okay, so far so good. So this implies, let's take any base point. This implies that pi 1 of R2 minus, let's take a point, say minus the origin, and 1, take a point 1, 0, let's say. This is isomorphic to pi 1 of R3 minus the origin. This is the origin in R3 with respect to the base point f of 1, 0. But however, remember we proved independence of base points. This is isomorphic to pi 1 of R3 minus the origin, and because R3 minus the origin is path connected, we can as well take the point 1, 0, 0. Okay. And now, what are these isomorphic to? Well, R2 minus a point. So here's a little lemma. Rn minus the origin deformation retracts to Sn minus 1. Okay, and this is easy to prove. Remember, we have to prove at each, we have to construct a family of maps which on Rn. So define H from Rn. So this is the, set the origin, Rn minus the origin to Rn minus the origin. That's with time, which at time 0 is supposed to be the identity, and at time 1 is supposed to map into Sn minus 1, and at all times it fixes n minus 1. Okay, and that is, we just use polar coordinates. So here is, for example, S1, and here is a line, and the line has a vector which is always has norm, which is we have taken, so we have a line and we are taking points away from the origin, so the norm is not 0. So we'll define h of s x and the time t. At time 0 this is just x, okay, but at time 1 it should be x by norm x. Okay, so you could write this as 1 minus t plus t times norm x. Perhaps we have to adjust that formula a little. Let's see, if t is 0 this is 1, if t is 1 this is just norm x. Okay, so and if norm 1 is this, so this gives a deformation retract. But since this is the first deformation retraction we are constructing, let's verify certain things. So let's look at h of x of x with 0 is of course x, and h of x of 1 is x by norm x, which is in Sn minus 1, and x belongs to Sn minus 1 implies that norm x is 1, which implies that h of xt, whatever time is going to be x by 1 minus t plus just t. which is of course x itself. So we see that this deformation retracts onto Sn minus 1, and hence we have the fundamental groups are the same. Okay, so that is the next thing that we will use. So it will follow from this that pi 1 of R2 minus the origin with whatever the base point is, it doesn't matter. This is isomorphic to pi 1 of S11. 1 here is the complex number 1, okay, which is isomorphic to pi 1 of R3 minus the origin with whatever the base point is, which is isomorphic to pi 1 of S2 and the point 1, 0, 0. Okay, now what do we have? Well, let's think what is the fundamental group of the sphere. Now it's kind of intuitive that if I took the sphere and I took any curve on it, then this can be collapsed to a point, unlike the circle where we don't wind. And this would not be hard to prove at all. It would be very easy, except for the fact that there are space filling curves. So if your path was actually surjective, then it takes a little bit of work. Okay, so this is isomorphic to Z, and we get our final contradiction by proving the following theorem, which is that pi 1 of S2 with 1, 0, 0, this is isomorphic to the trivial group, okay, which I can write as 1, or let me write it as just E, as the group with no elements at all. So this is the theorem that we will prove next. So let's look at a picture to prove this. Okay, there's the picture of the sphere. Let me draw it a bit bigger. Okay, I'll have another go at it. Okay, so we draw a sphere, and we will divide the sphere into regions. We have the tropics in the middle, okay, and the Tropic of Cancer and Tropic of Capricorn, and we will call this part as V plus and this part as V minus, and our base point x0 is going to be sitting here. Okay, and we have a path, and the path, maybe it goes here, there, this way. It may be space filling. It goes behind the sphere, wanders around, comes here, and maybe it comes this way. And we want to show this is homotopically trivial. Okay. The problem, as I said, is it might be space filling. So what we want to do is we want to break it up into paths that are not too big, that are under control. Okay. So our first step is going to be very similar to the previous one. So we take the interval 0, 1 here, and then we are mapping that by a curve alpha. So let alpha map 0, 1 to the sphere. Okay, by Lebesgue number theorem, following a by now familiar argument theorem, okay, we can subdivide uh, 0, 1. So I'm going to subdivide into intervals, and I'll just draw the pictures. I'll call them J1, J2, J3, etc. Subdivide 0, 1 such that alpha of Ji is contained in V plus, or alpha of Ji is contained in V minus, such that for all I. So this guy is contained in this. Okay, and finally, this is a nice trick, not really necessary here, but it's very nice in other situations. So if Ji and Ji plus 1 are both contained in V plus, you merge. Okay, what does this achieve? This achieves that alternate ones are above and alternate ones are below. Okay, and hence, if there is more than one interval, each intermediate point well, it is between an interval that's in V plus and one point is because it's in between an interval in V plus and V minus, it's in V plus intersection V minus. Okay, so now we have an arc. So suppose we restrict this. Okay, so this is say Ji. Well, this was actually in the equator. So it was not a very good picture. So let me not call this Ji. Let's take a real one. So for example, Ji could be this guy. It's not contained completely here. It goes up and comes down. In this case, the other one was adjacent, but it's contained exactly in this. Well, then I can find an arc in the equator, okay, and homotop it. Okay, so homotopic to beta I, hence is in V1 and Vi. This is the intermediate point. So both of these endpoints are in the equator. That's the important things. Hence alpha restricted to Ji is homotopic to beta I, and beta I is which maps 0, 1 to V plus, not 0, 1. It maps the same domain, Ji to V plus intersection V minus. Why is this the case? Well, notice that this alpha intersection Ji is, maybe it's contained in V plus, or maybe it's contained in V minus. Without loss of generality, say it's contained. So it misses the southern hemisphere. And V plus is D2. It's homeomorphic to the closed disk. And on the disk, any two paths are homotopic provided their endpoints coincide. So we simply find a path beta I whose endpoints coincide with alpha restricted to Gi and map it to that. So now what is the consequence? So using all these, by all these, alpha is homotopic to beta, and beta maps 0, 1 to V plus intersection V minus, which is contained in V plus, which is D2. Okay, hence beta is homotopic to the identity, because in the disk beta is a loop, alpha is a loop. We have only changed the endpoints of segments, so this happens. Okay, so to recapitulate, I didn't write out in words everything, but the picture is maybe a little more vivid. We have a northern and southern hemisphere, but I don't just take that, I include the tropics in both parts. I can break my loop into segments which are alternately above and below by simply merging them if they are successively. If there's one segment there's nothing to be done, then it's contained completely in the tropics. Otherwise, each segment is contained either in the upper or the lower. It misses one of the poles, as a result of which it's homotopic to something with the same endpoints, and its endpoints are in the tropics. So what we do is, by this it follows that your segment is homotopic to a segment contained completely in the tropics. So tropics is also contained in tropics union the Arctic Circle, or in fact the mid latitudes as well. Anyway, everything excluding the base, which is a disk. And so you have a loop which is contained in a disk, and hence it's homotopic to the identity. It follows that every element is trivial. As a result, the fundamental group of S2 is with any base point is trivial, and this argument works for any sphere of dimension 2 and more. So this has given us our final contradiction, right? So let me just write this. This is isomorphic to E, so this is a contradiction. Okay, with this we finish another nice application, and now we will move on to other kind of theory.